Hi, welcome to session 10 in our series on electricity and magnetism. Actually, we're going to be doing this in two parts. This is the first half of session 10, and we'll be looking at applications to motors. Now, we take motors for granted today. It's not flashy like a cell phone and other digital devices, but you'd be amazed how much we rely on motors to do things for us. I counted the number I have in my home and in my shop, and I counted over 100 motors. So I want to start with this array of tools I have on the floor. The tools at the bottom are pretty much what I had when I was a kid, and I'd help my mom with projects, or I'd make things for myself, and they were all hand tools is what I used. We didn't have any power hand tools till I was in my teens, and today almost every home has at least one of these, if not a whole bunch. This is not an exhaustive array of tools. Now, each of those power tools has a motor in it. Let's take a look at what's inside. I'm going to pick the drill. I think that's probably the most common tool, even if you're not a do-it-yourselfer. If you've got a power tool, I bet that's the first one that you got. So let's take a look inside of one of these. So right now, you're looking at a drill that you would plug in the wall. It's not cordless, it's a corded drill. And I'm going to run it at a low, very low voltage so you can see the actual rotation, and it's not just a blur. What is spinning is a rotor that looks just like that. The commutator, excuse me, an electromagnet. Now that is rotating inside of a electromagnetic field, a stationary electromagnetic field. The rotor fits in there just like that. And there's brushes here that convey electricity to the commutator. That's how the rotor gets its energy, through the commutator, which is tied to all these electrical windings, this magnet wire. Now, in some motors, instead of electromagnets for the field, we just use permanent magnets. So I have a north pole and a south pole. It's already polarized, and you put the rotor inside there. When you energize this with the brushes, the carbon brushes, it reacts with a stationary permanent magnet and rotates. Now, the thing about these motors have a lot of power in a small space. They're very compact motors. They put like I said, they pack a lot of power in a small package. Now, the thing about power is it consists of two things. You have torque and revolutions per minute. Power is proportional to the product of those two. These motors have a lot of RPMs. They don't have a huge amount of torque in their tiny packages. What is torque? You're probably not familiar with that word. Torque is like a rotational force. So if I have a screwdriver like this and I'm turning a screw, I am applying torque. This is force, but this is torque. If I need a lot more torque, I might put a wrench on here and apply even more torque. I've got leverage. Think of torque as leverage. Or perhaps I have a tiny little screw and I just need to tweak it a little bit. This doesn't take a lot of torque. Now, if I'm drilling holes in a piece of steel, I might need a lot of torque. Or if I'm using a big flat bit, like this one here, I'm going to need a lot of torque. If I were to connect the bit directly to the shaft of the rotor of one of these motors, especially when they've got a small rotor like that, I'm not going to be able to drill the wood or the steel. I need more torque. And the way we get more torque out of these motors is we have a gearbox. That's what this piece of aluminum casing is holding. There's a gearbox in there. And notice that the speed of the chuck is much slower than the speed of the motor. We are trading speed for torque. Let's take a look at how we do that. Here's another drill. This is a cordless drill. It's a little bit different in construction, but the pieces are all there. There's the motor, there's the chuck, and in between is the gearbox. I'm going to run the motor. Now we don't have my hand in the way. And let's turn this light on so you can see the gears. I think I want to zoom in a little on that. Now you can see that little gear there is connected directly to the motor, and it's really spinning relative to these other gears. So that little gear is turning this big gear. This big gear is connected to the little gear directly on the same shaft, and that little gear turns this big gear. Now the ratio of their speeds is inversely proportional to the diameter of the gears. So I'm going to stop that for a minute. Let's measure the size of the gears. So this gear is that big, and I think the other one is identical. It looks like it's about the same size. So those two gears are 1.5 inches in diameter, okay, from here to here. Now these little gears are about that big, which is pretty close to about 1/4 inch. Okay, it's about 1/4 inch. So 1, 2, 3, 4, 5, 6. So the little gear is 1/6 the diameter of the big gear in both cases. So what's happening is I've got 1/6 the speed in this step and 1/6 the speed here in this step. That's 1/36 the speed, but my torque is multiplied by 6. So I have 6 times the torque here and then 6 times the torque here, which means at the chuck end here I have 1/6 the speed and close to, 1/36 the speed and close to 36 times the torque minus whatever frictional losses I have in the gearbox. So that's how we're able to take advantage of the fact that these little motors produce a lot of power in a small package, but at a very high RPM and low torque. We use the gearbox. Now it's not just the drills that have that gearbox. Here is a circular saw. We're spinning a saw blade. Where did I put my saw blade? There it is. We're spinning a saw blade about that big. If we connect that directly to the motor that's in here, relatively small motor, it would just get stuck. It would not continue to turn. Now I've got the gears and the motor from a saw exactly like that. Let's take a closer look. So here's the motor, and here's the gearbox. And I'm going to run this for you at a very low voltage. There's the motor speed, and there's the speed that we would attach the saw blade to. Okay. It's about a 4-to-1 ratio. And this really is the same motor and gearbox that came out of that, that power saw. It was an identical version. Now let's take a, see if you can see the, let's take a look at the gear. If I can hold this right, you can see the gear right there. That's the big gear that drives this shaft here. And then there's a little gear right here connected directly to the motor. You see it's in line with the center of the motor. And that drives the big gear, about a 4-to-1 reduction, so that we can use that saw blade to actually cut wood. Now it's not just in power tools like you use in a shop that we have this kind of technology with these high-speed commutator motors and the gears. So here is a mixer, okay, kind of a low-end mixer, and let's take a look at what's inside. Notice the motor. Let's run it. There's the commutator that takes the electricity into the rotor. These are the field magnets. It's an electromagnet. The coil is down below. You can't see it. It's a single coil in this case. It still accomplishes the job. And then at the end of this shaft is a worm gear. It's like a screw. It's like a spiral. And as it turns, it moves these little white plastic gears to turn the mixer blades. Let's get this up a little closer. And you can see the plastic gears here. They got some goo on them. They've got grease on them so that they'll run smoothly. Let me see if I can show you the worm. Can you see the worm gear right there behind the little fan? I'm going to stop it. And you can see that spiral in there. So even in your kitchen, you've got versions of this. And the last thing I want to show you is a paper shredder power source, or mechanical power source. So here is this little tiny motor. Look at the size of that motor. It's like twice the thickness of my thumb. And the little gear is right on the motor, spinning away, turning this larger gear, reducing the speed, increasing the torque, and it's connected to this little gear. And as that little gear turns this big gear, again, it reduces the speed but multiplies the torque. And then there was one more stage that ran off of that steel gear, which turned the actual tumblers that would shred the paper. Now the reason that's a steel gear is because by that time the torque is so high, you don't want it to just be little pieces of plastic. It would break. The power, or the rotational torque was so large that if you did it out of plastic, it would wear out quickly. So that's kind of the world of these power tools using the commutator type of motor. In the second half of session 10, we're going to take a look at how this rotor evolved, how it works, and how motors in general work. Okay? So I'll see you then. Take care.